Hi, and welcome to MSc. In this lesson, we're going to talk about calculating empirical formulae. When we're asked to calculate an empirical formula, typically we're given percent composition. That could be of a compound, such as this example, or it could be the percentage of a sample itself. Here we're given an example where we have 58.8% carbon, 9.9% hydrogen, and the rest is oxygen. So what that means is our very first step needs to be to calculate the percentage of oxygen that we actually have. And of course, we know that the whole sample has to be 100%, so calculating the oxygen amount is not super difficult, but it is important to remember that we're not short information. We just have to do a little bit of calculating before we can get started on the actual calculation of the empirical formula. So this gives us 31.3% oxygen. The next step is that we're going to assume that we have a 100-gram sample overall. The reason we do this is because this allows us to convert our percentages into masses. So now I have a mass of carbon in this made-up sample of 58.8%, not percent, but grams. This will allow us to do our mole calculations. So now I have 9.9 grams of hydrogen, and for my oxygen, I will have 31.3 grams. So again, it doesn't matter that the sample is not actually 100 grams. It doesn't matter what it is. If we can calculate moles based on this, then the ratios will all hold true. But the 100-gram sample allows us to convert directly from the percentages into masses. What we have to do next is calculate moles. And we're going to do that using our mole formula, where the number of moles, the lowercase n, is equal to the mass in grams, the lowercase m, divided by the molar mass, which is in grams per mole, and it's the capital M. And we need to do that not once, not twice, but 3 times for the 3 different elements that we have present. If your sample or compound only had 2, you'd only do it twice. If it had 4, then you'd have to do it 4 times for each element that shows up. But as you can see, we have 3 identical formulas here, and that really can't work in the same problem. So what we have to do is add something to these to illustrate our work more clearly. I like putting subscripts on these to show that this is going to be our carbon, this will be our hydrogen, and the last one will be our oxygen. There are other techniques of showing your work or identifying which element belongs to which equation. You can use brackets and whatnot, but I like the subscripts when it's nice and simple with just letters like this. So let's start working through these examples. We have the mass of carbon, but because we assumed that 100-gram sample, we have 58.8, and the molar mass of carbon from our periodic table is 12.01 grams per mole. That gives us a number of moles of 4.8959, and then the number continues on, and I'll use the ellipse to illustrate that. We don't want to round this number. We want to be really careful how we round numbers as we go through. And this is, of course, in units of mole. We can now go for the hydrogen, and we can say the mass of the hydrogen that we have in our 100-gram sample is 9.9. Molar mass of hydrogen is 101 grams per mole, and that gives us a number of moles of 9.7920, and again it continues on, and that is also in moles. Again, we don't want to round quite yet. And then the oxygen, its mass that we calculated was 31.3 grams. We fix that, make that look a little better. 31.3 grams. And the molar mass is 16.00 grams per mole. That gives us a value here of 1.95625, and I'll write the whole thing because I noticed that it is a terminating decimal, and that is also in mole. The next part of this is where we now need to create a mole ratio. So we'll write out a mole ratio here, and we'll say, okay, we have the ratio of moles of carbon to the moles of hydrogen to the moles of oxygen. And we're not going to write these numbers, but we're going to look for the smallest number that we produced here. And of course, the smallest number that we produced is this one here. So we're going to divide all of these numbers by that number. So we're going to divide by the smallest. All right, so that means that our ratio down here, the number of moles that we'll have of oxygen down in this spot, will be 1, because any number divided by itself will just be 1. Working backwards across the way here, when we divide 9.79 divided by this 1.95, we'll get a number very, very close to 5.0055, I believe. So that is something that we can comfortably round, and now it's appropriately to do so. We'll round to 5. Then we'll take our moles of carbon and we'll divide by the moles of oxygen. And when we do that, we get a number that is very close to 2.5. I think it's 2.502. Continuing on. That rounds to 2.5. We have to be careful with rounding here. We want to look for numbers that will round to a half, maybe a third or 2/3, numbers that might round nicely to a whole number like the 5 did, or ones that might even round to a quarter or 3/4. So be really careful with rounding here. You don't want to round too aggressively at this stage. So eventually these ratios will form our subscripts on our empirical formula, but we can't have a subscript of 2.5. So what we'll do at this stage is we'll look and see if we have to multiply. And we do have to multiply here. And we're going to multiply such that this will produce all whole numbers. So the only one that's not is the 2.5. And because it's 0.5 like a half, multiplying by 2 will take care of that. And what that produces for us then is a ratio of 5 to 10, which is 2 times 5 to 2. If we'd had a decimal like 0.3 repeating, then or 0.6 repeating, then multiplying by 3 would get the job done and get us to the whole number. If it was a quarter or 3/4, we'd multiply by 4. And so we want to be very cognizant of that while we're working through these questions. We can say, therefore, that the empirical formula for this unknown sample of hydrogen, carbon, and oxygen would be carbon 5, hydrogen 10, and oxygen 2. So this is the empirical formula that we found for this example. Keep in mind, this gives us different information than a molecular formula. Molecular formula, the subscripts refer to how many are in the actual compound, right? 5 carbon, 10 hydrogen, 2 oxygen. But in this case, this is an empirical formula. And this empirical formula only tells us the ratios that we've calculated. So we have to be cognizant of that difference. That is a big difference between the two different types of formulae. So that is how you calculate the empirical formula for an unknown substance from a percent composition information. I hope you found this video helpful. Thank you so much for listening, and thank you for watching.